Okay, we've been talking about the mean field model of ferromagnets, and we've used this model so far to find the magnetic susceptibility of a ferromagnet when it's above the Curie temperature. Okay, when it's above the phase transition temperature where it turns into a paramagnet. And let's go on now and see how the mean field model can also predict spontaneous magnetization. Hang on. There we are. So we developed an expression for the magnetization, which led to an expression for the susceptibility in the limit that the temperature is above the Curie temperature here. And we found that the susceptibility increases as the temperature decreases towards the Curie temperature and finally diverges at the Curie temperature. Below the Curie temperature, the system exhibits spontaneous magnetization. We don't need any external field to get the spins to line up. So now, let's see if we can use mean field theory to understand that. All right, so what we mean by spontaneous magnetization is that the magnetization is not zero, even when the applied field is equal to zero. And we can analyze this first by recognizing that if the applied field is zero, then the effective magnetization, the effective magnetic field is just lambda times the magnetization in the mean field model, okay? Then we can use this effective field in the magnetization model that we developed for paramagnets. Okay, which says that the magnetization is just mu b times n times the hyperbolic tangent of mu b times the magnetic field divided by kT. Only now, this is the effective magnetic field, okay? And to understand what this equation means now, we have to look a little bit more carefully at it and even rewrite it to make it simple enough that the behavior kind of stands out to us. So that's what we're going to do in the next few lines. So we're going to notice a couple of things. First of all, this term mu b times n, that has a physical meaning. It's actually the magnetization we would get if all the spins pointed in the same direction. In other words, it's the maximum magnetization. The second is, well, we've already noticed that B effective is just lambda times m. And furthermore, we should remember from our previous discussion that the Curie temperature is defined in terms of lambda. It's lambda times the Curie constant divided by mu naught. And the last thing we'll need is the Curie constant itself, which we developed when we talked about paramagnetism, and it's n times the Bohr magneton squared times mu naught divided by k. Okay, using these ingredients, we can rewrite the formula for magnetization. First, let's write this as m max times hyperbolic tangent of mu b, and then substituting for B effective, we have lambda m divided by kT. Okay? And that looks pretty good. It's a little complex, you know, because look, the magnetization appears on both sides of the equation. Okay? We can make the behavior even more clear if we rewrite this a little bit more. Here, let's focus on the argument of the hyperbolic tangent function first. So the argument of this function is equal to mu b lambda m over kT. But you know, lambda can be written in terms of the Curie temperature using one of the formulas that we've written down a moment ago. So let's write this as mu b, and then we'll write lambda as the Curie temperature times mu naught divided by c. And then in the numerator, we still have, denominator, we have K Boltzmann times T, and then we have our factor of M. Okay? Now we have the following. We have TC divided by T times what remains here. Oops. Mu B, mu naught over C times K Boltzmann times T. Of course, C is just N mu B squared, mu naught divided by K, so that K Boltzmann goes in the numerator. Then we have all of that times K Boltzmann in the denominator. And now notice that lots of things cancel out. So the mu naught cancels out, K Boltzmann cancels out. This factor of mu B cancels with that factor of mu B. And in the denominator, we're just left with N times mu B, which of course is the maximum magnetization. So in that way, we can write this as TC over T times M over the maximum magnetization. That's right, they're simple looking now. Summing up then, we could write the magnetization divided by the maximum magnetization as hyperbolic tangent of TC over T times M over the maximum magnetization. Perfect. Okay, so there's a simple looking equation that describes the magnetization of a ferromagnet and implies, we'll see, spontaneous magnetization. Now, if we could solve this equation, we could find the magnetization, M. But there's a problem with this equation. M appears on both sides. And on one side, it's in side of a hyperbolic tangent function. It doesn't look like there's any way to analytically solve for M, okay? So instead, we're going to have to solve for it numerically or graphically. And actually doing so has a lot of meaning. So let's solve it graphically here and see what we get. In order to solve it graphically, I want to rewrite this formula just a little bit more. Let's let the argument of the tangent function, hyperbolic tangent function, be x. Okay? Then you can see that if I rewrite my equation, on the right side, I'll have hyperbolic tangent of x. That's nice. And on the left side, I have m over m max, which is just t over tc. I'm sorry. Well, let me write it again. I have m over m max. And now I can multiply and divide by this term. Okay? So that when I do that, I have on the left-hand side, I have t over tc times x is equal to hyperbolic tangent of x. There's another way to write our formula, provided that we remember what x is, right? But the nice thing about this second way is that it's easier for me to sketch, okay? So now let's make a sketch and see what this means. in my sketch, the x-axis will be x, the argument of the tangent function, and the y-axis will either be the value of the right-hand side of the equation or the value of the left-hand side of the equation. Okay? First, let's sketch the right-hand value side of the equation. That's the tangent function, hyperbolic tangent function. Okay? So that begins from the origin with a slope of 1, and then as x gets larger, it kind of curves over and asymptotically approaches the value 1. Now, what about the left-hand side of the equation? Well, the left-hand side of the equation is clearly just a straight line. And the slope of the straight line is t over tc. So we can imagine a couple of cases. First, suppose that t over tc is greater than 1. And we're at a temperature above the transition temperature. In that case, my line has a slope greater than 1. And because the hyperbolic tangent starts out near 0 with a slope equal to 1, that means that the red line and the blue line never cross. So again, the red line is the left-hand side for t greater than tc, and the left-hand side, the blue line, is the right-hand side. Okay? And for t greater than tc, the only place they cross is at x equals 0. So that means for t greater than tz, with no applied field, the only solution is m equals 0. If x equals 0, then m must be 0, right? Well, that's not so exciting. How about the second case? What if the temperature is less than the Curie temperature? Then I have a line, but the line has a slope less than 1. There we are. Now you see that there's another solution. The left-hand side and the right-hand side cross at a finite value of x, meaning a finite magnetization. So now we have two solutions. And they're m equals 0, that's one solution, this one, and the second one. And the second one denotes spontaneous magnetization. Okay, so spontaneous magnetization arises even in the mean field model, and we can see how it does by in the analysis that we've just done. All right. Okay, here. Let's pause here.